number 13, known as Gay Genie, and you'll know what that means during the presentation.
How's it going, everyone? Like Professor Pisano said, we're Team 13, Terence Black, Gerardo, Ravago, Terence, Galasso, Ratkhan, Saginbazarov. My name is Dan Taylor. So the point of this project is, well, imagine you have this facility and you want to keep track of people parking in your parking garage. But you want to automate the payment process. You don't want to have people interacting with, staff or whatever. They can just go in and you keep track of how long they're in there and what they're doing and when they're allowed to be in there, and handle payments from them and basically make it a completely seamless operation. That's essentially what the customer we're working for has done. They've created the software to allow you to do that. It's we'll talk about it in a second, but it's automation of the payment process. We're creating the hardware interface that bridges the gap between the hardware that's already there on the site and the software that they've written. So this is the customer. It's a hardware integration company called ITS down in Connecticut. Basically, they created all this software in the form of a smartphone app that can sort of centralize all your payment needs and all that, and can keep track of all the open spaces. They've all already implemented some of their technology and facilities in New Jersey and places like that. But basically, what they're going for with this and proposing this project to us is to kind of get the ball rolling on this whole automation of the parking garage, parking facility for corporate offices and all that kind of thing.
All right. So this is how we're going to do this. I'm going to give a brief system overview. Basically, we have two PCBs, a main PCB, and a bunch of daughter cards, which make our system expandable in blocks of 4 in, 4 out GPIO ports. This is going to be suitable for the installation environment. We put it in an EVA4 enclosure, so it's weatherproof, and we've also made it web configurable, so you can plug into our server on our gauging unit and configure its location data, and also set all the methods and whatever you need to do. Here's our block diagram for the system. As you can see, there's the main PCB in the middle. Attached to that is our Raspberry Pi onboard computer, and we have these GPIO blocks to your left. Those are connected by an I2C bus, and Raspberry Pi just pops onto our main PCB, some header pins. There's also a GPRS unit for using a cellular connection to control the unit, and we also have an Ethernet connection for a more reliable TCP/IP connection. This is a picture of our finished unit. You can see it outside on our table. This is our main PCB off to the right. And our daughter card is over there. Those are actually 2 daughter cards stacked on top of each other. And yeah, each daughter card has a bunch of relays, which can be toggled on and off remotely. And yeah, as I mentioned, Raspberry Pi is our main computing element. It hosts our web configuration page and the server, which accepts TCP/IP commands for controlling the GPIO boards, as well as sending those commands off to the GPIO boards, and basically just the central part of our project. And now to Terry's lab.
So we developed 2 main programs. One, the client that runs on the Raspberry Pi, which listens on the TCP socket for commands that we send it. It accepts a TCP connection and launches a new thread, and depending on the command that it receives, it executes the appropriate action. We'll hear more about the commands later. And the simple server that we developed runs anywhere else you want it to, and we just developed that to prove that you can actually control this through TCP. So these are the commands. Okay, so the 3 commands are detect, output, and input. When you run detect, you're pretty much pulling the I2C bus for which boards are attached, and that changes depending on which ports you have connected or not, and that changes dynamically. So if you have the server already running and you just make a board, it'll give you a different result. Output board and function. So we use that command to control the output relays on our daughter cards. So the boards are numbered, of course, and you send it a byte and hex. And what we did as a test is hook up LEDs to the different relays and represent binary values on them. And input, will read the current input status on the boards. So the daughter cards have output relays and input relays. You just read the inputs for that one.
This is how we implemented it. We used an I2C bus for expandability, so you can connect as many of these devices as you want to the I2C. It allows for theoretically up to 2 to 7, 128 devices. Currently, we have it configured to have 4 unique GPIO boards, which can be configured upon setup. To do this, we use the wiring Pi library for the Raspberry Pi. This gives us some functions to read and write to specific I2C addresses, so we can send bytes or receive bytes. It also lets us set GPIO pins and get interrupts from the GPIO pins, because we also will have these boards wired to certain pins on the Raspberry Pi, so it can ask for the Pi to read in the inputs whenever an input changes, and then that will be logged onto our Raspberry Pi. On each of these boards is an MSP430, and on that is a USI module where we implement the I2C communication and the GPIO pins and all the unique board configurations for addressability. And now we're going to talk about our web configuration.
For web configuration page, we create a simple web page that runs on our live web server on the Raspberry Pi. It has input forms and data from which will be saved on Raspberry Pi that will be used to configure the unit. And since we're running on Raspberry Pi, which has full Linux distribution, ensuring VPN connections that our customer required is no problem. We'll install the open source open VPN client, which will be able to connect to VPN server. That's it.
Okay. So the main PCB acts as the central hub between all of our components. It holds the Raspberry Pi, which is stacked on top, and connects to the daughter boards through headers. And the SM5100B is the GSM/GPRS chip, which I'll talk about later. So here's our schematic for the main PCB. See our array of voltage regulators. So this chip serves as our backup network interface in the event that we don't have our Ethernet connection. It's capable of sending and receiving TCP, UDP, and in our testing we've been able to send and receive TCP and UDP packets, and send and receive text messages as well. So that can come into play if our customer decided to develop it further. They want their unit to warn someone when they're low on time for parking. You can send them a text message to cooperate with their smartphone app. So on the main PCB, we have our array of voltage regulators to provide 3.3, 4, 5, and 12 volt lines. The 3.3 3.3 line is used to power the microprocessors, which are on the daughter cards, and that's routed through the daughter board headers. The 4 volt line is used exclusively for the chip that I mentioned in the last slide. The 5 volt lines also get passed to daughter cards. So we developed, or rather we hacked together an AC adapter, which we use to provide our power to this array, and we need all this lines.
Another one of our customers' requirements was that the system had to be able to run off a backup battery. They provided us with the battery you see here, the 12 volt lead acid battery, and it has 7 amp hours. So theoretically, I think the requirement was for 7 to 8 hours. It should be able to last that long. And it's enabled by a MOSFET switching network, kind of a power multiplexer, if you will, because we didn't want to have any kind of smart system to enable the battery, because if the power goes out, then your computing devices will shut down after a short amount of time without power. So this network has 4 MOSFETs, and it's able to safely turn on the battery without ever interrupting power to the computing source. So you can always have at least 12 volts passing either to the regulators or right to the board through the power section. You can never lose power. There's also there is a charging system with this, but it has a few safety features that needed to be built into coding before it was fully ready to use. It's a boost converter, microcontroller regulated. A few things like maximum timeout and really a temperature sensor or something that we'd like to add to that for future versions of this to really make it fully reliable and safe. So with lead acid batteries like this, I'm sure a lot of you know things can go awfully wrong if you charge it too long or something like that, or if it gets too hot. Okay, so this is the board in charge of interfacing with all the peripheral hardware. So some of you might already be thinking, okay, well you have a 12-volt battery that you can pull an amp or so out of. I mean, you can obviously pull more out of it, but for a short amount of time. It should be noted that this system is only really meant to power itself. The signals that come out of it, like the ones that come out of this board at 12 volts, are input signals to other hardware that's all powered independently. So we're not actually driving a gate or anything like that on site. That stuff was told, we were told that that's all powered independently, that we're just sending a signal out to it. So essentially what this board does, I designed this board to take a signal from a controller that is already used to operate, for instance, a parking gate or other peripheral hardware. You might see a strobe light or a buzzer that tells you when someone's exiting your garage so you don't crash into them or you don't run over someone. Essentially, those signals, we pull a line out of that, send them to these input channels. That gets sent into this microcontroller, so that way we can issue interrupts and we can keep track of when these actions are being performed, like if somebody's entering this facility. So we have a master device, and we give I2C lines to all these boards. They just daisy chain together on these headers. And basically we send signals out from the output channels. It's just a BJT switch to these relays, driving the relays, and turns on these output channels at 12 volts. So the 12 volt line is obviously the biggest one we need, and that's regulated from one of those buck converters that we have on the other board. So this is the schematic for that board. This PCB design actually went through 3 versions. The first version was pretty simple. It was meant to have one board operated from the computing block. So in the second version, I completely kind of modularized it. You can make any board, any address, and you can use any of the interrupt channels with any board. It basically kind of just made everything not so unique to the individual device. The third version, which we didn't produce, had a few corrections based on forwarding the headers to each other. So that will be released to the customer in case they want to further develop it. But the second one works, and that's what we have mounted inside the enclosure over there. So it worked well. We're able to stack a few of them on top of each other too. And we were able to kind of get around the issue of getting all kinds of noise on our lines. You might think, well, if you're flipping relays on and off, then you're just kind of throwing a bunch of current into traces everywhere. With internal pull-ups on Raspberry Pi, we're able to damp that down so that we don't start ruining our interrupt lines with driving current all over the place.
So now the microcontroller on that daughter card that I was talking about is MSP430G2302, and its job is to implement the I2C state machine and have programmable addresses and programmable interrupt lines to the Raspberry Pi. It processes the commands input to either read the input and send it over to I2C bus, or process the command to set the output lines as necessary. It can pulse the output lines for a given amount of time, or just set the level on the outputs, and it just needs to generate interrupts on these interrupt lines we were talking about, so that the Raspberry Pi will know to read that for the change of input that happened. This is an I2C state machine that had to be written because this is a very cheap microcontroller that doesn't have a full-fledged I2C module built into it. It's basically a shift register, and you would just have to shift bits in and out to do the I2C. So that's basically our system in a nutshell. For any questions, you can ask us now, or visit our customers' websites for further information. Okay.
is this integrated into MK? And if not, how do you actually integrate?
What was that?
How do you integrate this into the MK? So somebody goes up to a gate, pays for something, and then has the gate open. What
Right.
is-
So the point of it is that the GPIO controls the hardware, but then everything's logged. So all that logging information can be associated with an account that was read from a card reader or something, whatever device you're attaching it to. And all that information can be pushed to their system. So you know who it was, if they're allowed in, and if they were allowed in, when they're in and when they're out. And that's how all the payment processing can be done. So all that information will just get forwarded.
You do this through the GPRS.
Oh, well, through the Raspberry.
Yeah, the Ethernet connection is the primary connection. So we use that.
Thank you.